Okay. Hi, everyone. I hope everyone can hear me properly. So, right. I hope you're all having a great time. My name is Guillaume, and today I'd like to talk about Scala.js and board games. So, board games are really fun. The thing is, some of them come with these um, score sheets. So you get one pad in the box, and if by any chance you happen to spend all your evenings on a single game because you're, I don't know, locked down because of a pandemic, which is also a great board game, by the way, then you use those pretty fast. So the idea I had was to replace the score sheets for Seven Wonders using a progressive web app and to implement that web app using Scala 3 and Scala.js, and also a library called Scala.js React. So a progressive web app is essentially a web app that feels like a mobile app, and then Scala.js is a way of building web applications with Scala. It's a compiler that combines Scala code to JavaScript, and Scala.js React is, well, a library that lets you use React from Scala.js. Could I have used a piece of paper instead? Absolutely. Is this over-engineered? Absolutely. But look at it. It's absolutely cool. So the idea is to have this this mobile app that you can open like any mobile app. And then when you open it, you can choose a game. Here, only Seven Wonders is supported. Have a list of your most recent games. Create a new game by adding a few players, and then once you have added all these players, you can enter the score that each person scored in each category of the game: science, military, treasury, and so on. Science actually has a special input because the rules for calculating score are slightly different. All other categories work the same. And then once you reach the end of this form, you can finish the game, mark it as finished. And the idea is that even if you close the app and open it again, you get a list of your most recently played games. So you get the kind of persistent storage that you would expect from a native web application. So this is what I've built using Scala.js, and today I will talk a little bit about how I did this and some of the problems I have encountered. So why Scala.js? Well, I think that you can't oversell a great type system. You're probably all familiar with Scala, so I don't need to try too hard to convince you of that. I also think that while Scala.js is certainly not the only way to get a type system for JavaScript, TypeScript is unsound by design. It sounds a bit harsh, but it's actually listed as their non-goals in their documentation. TypeScript doesn't have a goal of applying a sound or provably correct type system. I also think that JavaScript lacks a decent standard library. I think the popularity of helper libraries like Lambda or what was it, Lodash, show that well. Also Immutable.js, which provides immutable data structures that JavaScript doesn't have by default. And I happen to know and love Scala, so it was an easy choice to make. Getting started with Scala.js is relatively easy. You just add a SBT plugin to your SBT project, and then I've also added a dependency on Scala.js DOM, which is completely optional, but it will give us a nice statically typed interface to the DOM to do some cool stuff with. And now what I want to do is code something really, really simple. So I want a web page that displays hello ScalaCon, and then fetches the weather from an external API and prints it on the page. The way this is going to work is the first thing we need to know, what we need to do when approaching these kinds of applications where you need to fetch data from external data sources, is to define facades. They are similar in spirit to TypeScript type definitions, and they allow us to call JavaScript from Scala using a statically typed interface. It's relatively easy to define such facades. You only need to define here 2 traits, one that corresponds to the response of my weather API, and that trait itself depends on another trait, which represents a single item in that response. And both traits are annotated with a special annotation that tells the compiler this is a facade to something that exists in the JavaScript world. And so these traits have no runtime cost. They are only useful to the compiler. Then the rest is very much like your good old JavaScript. If you already know JavaScript, then this code should feel immediately familiar. Everything is very close to JavaScript, from the DOM methods like append child to the fetch API, which lets us call our external weather API and get a response in the form of a promise. However, I don't like that code so much. I think there is room for improvement. Because the thing is, it's just like JavaScript, which is good because it's easy for a lot of people to get started. You'd be surprised how much a Scala.js piece of code can be really, really close to the equivalent JavaScript code. But at the same time, because it's just like JavaScript, it also inherits a few of its quirks. So specifically, what I don't really like about that code is that it is highly imperative, meaning it is expressed as statements that manipulate the DOM in a precise order. And as applications grow, keeping track of that order of execution gets trickier, and refactors can introduce regressions in the program's behavior. That code also uses mutable properties, which is a symptom of the imperative nature of the program. So if you want to change what is displayed on the screen, you do that by actually mutating the text content property on a DOM node. This looks rather innocent in such a trivial program, but mutable properties like these can make larger applications harder to understand and expose you to subtle concurrency bugs. And finally, it has unsafe access to a list head, which, fair enough, is not really a JavaScript issue. It's more an issue with my code. But it's just a way of saying that sometimes just because you statically type something doesn't mean it makes your code perfect. My point of view is that since we have the full power of Scala at our disposal, we should aspire to more than just a statically typed DOM. So, well, don't get me wrong. I think Scala.js DOM is good, and I think that having types to manipulate the DOM is already miles better than doing it in vanilla JavaScript. But Scala is a powerful language, so why not use it to build something maybe a little more easy to maintain? So let's take a look at Scala.js React. Scala.js React is a library that lets you use React, the popular JavaScript library, from Scala.js code. It offers statically typed DOM elements, just like Scala.js DOM, although the domain-specific language that Scala.js React uses to define these elements is a bit different. But a major difference is that in Scala.js React, UI elements are data, not statements. And because they are data, it means that you can use pure functions to map your data, your domain data, to UI elements to form your view layer. UI and behavior are packed together in reusable components. These components have a life cycle that lets you run side effects at specific times. For example, when the component is first rendered into the DOM. And so when you have the view layer expressed as a pure function from data to UI elements, your component props, which is just pure data, and your component's lifecycle methods, you can put all of that into a single reusable component that you can use multiple times in your application. At the end of the day, Scala.js React is, well, React and Scala. So it has everything there is to love about React, like reusable components, one-way data flow, the absolutely massive ecosystem of React, and also everything there is to love about Scala, like case classes, algebraic data types, which now have a shiny new syntax, immutable data structures, union types, a rich ecosystem, extension methods, which also have a shiny new syntax. And it also provides a bit more than this. Because this is React and Scala.js, the library actually uses quite cleverly the features of Scala to provide an additional safety layer on top of the original React API. So you get a few things that you don't have in vanilla React or even in React with TypeScript. Specifically, you get referentially transparent callbacks, which will be very familiar to those of you who are already familiar with, let's say, IO Monad. You get optional integration with the Cats library, which is awesome. You get automatic performance management using a type class that can be used to compare the props of your components to determine whether or not they need to be re-rendered again into the DOM. And if they don't need to, if the props are the same, then the library automatically ensures that unnecessary renders are avoided. There is also an included router, other features as well. It's React and Scala and even a bit more than this. So now that I have introduced the tools of the trade, let's talk about the application itself. It's a very straightforward application, as you will see, and as you've seen already in the demo. And this application essentially has 4 pages. The 4th page is a bit different because it has multiple steps, but it is still treated as a single page. I will refer to it as a single page. So there is a home page with a 7 Wonders button that you can tap on to get to the 7 Wonders page, which has a slightly different design. The idea was to support multiple games in the future and have each game its own, and that each game will have its own section with its own specific design. So you can get to the 7 Wonders page, and once you are on that page, you see a list of the most recently played games, and you can tap on the plus button to get to the new game page. On the new game page, you get this opportunity to enter the names of the players, and if you have at least 2 players, then you can tap on the plus button once again to get to the next page, which is the game page. And that game page can also be accessed from the 7 Wonders page to edit an ongoing game. If, for example, you've closed the application before you entered all the scores. So at this point, we know that we will have 4 pages. So we can already start to model our routes using a nice new feature of Scala 3 called Opaque Types. And modeling routes this way brings a few advantages. So the idea is that inside this route module, or this route object, the type route is seen as a regular string. But outside of this module, string and route are treated as incompatible types by the compiler. So as a consequence, it is impossible to obtain a value of type route except by using one of the values/methods defined in this route object, which means it is impossible to link to a non-existing page unless that module itself exposes non-existing pages. And this additional type safety is provided at no runtime cost, because at runtime, a route is just a regular string. So in that module, I have defined the opaque type route and the few routes of my applications: the home page, the 7 Wonders Last Games page, the new game page, and also a method that takes a single game ID and outputs the URL, or rather the route for this game, the page that lets you edit the scores for that single game. So we have identified a few pages. Then we can also identify reusable pieces. So we know that this app will have a page background that comes in 2 variants, the 7 Wonders variant and the green felt variant, a navbar that also comes in 2 variants, and this navbar can also hold exactly one of 3 possible buttons on each side. So wait a minute. I'm sure this is starting to feel a little familiar to some of you. And if you've seen Nicolas Rinaudo's talk back in May, then you know that this is a perfect use case for algebraic data types. So in this file, I'm using new features of Scala 3, the new ML-like syntax without the braces, which I really, really like, by the way, the new enum syntax for ADTs, and the new union types, which will make our components slightly more convenient to use, as we will see in a minute. The idea is that side items, which are really side buttons, for our header or our navbar, only come in 3 variants. Each variant is bound to a single action, and these actions can only be one of 3 things. The new enum syntax in Scala 3 makes it very, very easy to model this kind of data. And similarly, the navbar itself only comes in 2 variants, a wood-like variant and a marble-like variant, again modeled using enum types. And then the case class called props is, well, the props that you need to feed to your component so that React can render it into the DOM. Once you have these data types defined, it becomes a game of transforming data into DOM node. This is where algebraic data types really shine, because illegal states become impossible to represent. It is impossible, for example, to pass another variant to our navbar than wood or marble. The header style is one of these things and cannot be anything else. And at the same time, the compiler compels you to handle all possible cases using exhaustive pattern matching expressions, which means that your UI is correct by construction. If we look at the code, we have one function that maps navbar styles to CSS classes that have been defined in a CSS module somewhere else. we have one function that maps actions and a single DOM node to another DOM node, again by using an exhaustive pattern matching expression. We can associate each action to either a link or a span element. By the way, I'm using Next.js in this application. This is largely irrelevant for the rest of the talk, but if you are wondering what is this next link component, it is simply the component that Next.js, a framework built on top of React, uses for navigation. So I'm using this rather than a traditional link element. And then I have a third function that associates a single item, a side item, to the corresponding DOM node by rendering the by associating each action with a unique icon, and then rendering by associating each side item with the corresponding icon, and then rendering the action using the previously defined render action function. So it's all this idea of first define the data type, and then your UI just is a pure function from data to UI elements. The header component itself is essentially a function that maps the props of the headers that we have previously defined to DOM elements, with just a tiny bit of React boilerplate around it. So it's not exactly a function, it's a functional component to which you pass a function to tell React, hey, whenever I ask you to render this component into the DOM, what I want you to do is actually take these props and turn them into these UI elements, and then render these UI elements into the DOM. And React will make sure that whenever the props of the component change, the DOM is also updated, because that is essentially what React does. And then once you have a few reusable components like header, assembling pages is a lot like assembling Lego bricks. So for this games page, all we need to do is take the page background component and stack the header component on top, and then stack the game button element on top of it. And there you have it, a fully functioning games page. But the thing is, not all pages are that simple. So for the games, for the 7 Wonders page that displays the last played games, what I need is to fetch data from an external data source. And so I need to answer the question, where does this data come from? The idea will be a lot like the weather component that I have shown earlier. We need a way to hook into the page's lifecycle to tell React, whenever this page is displayed, I want you to go fetch the data that I need and provide it to me, to my view layer. So this is how it will go. Imagine the user is on the home page. They visit the 7 Wonders page by clicking on the 7 Wonders button, and then the 7 Wonders page is loaded with an empty list of games. This empty list of games is the initial state of the 7 Wonders page. And then something happens, magic. The page's state is updated, and it is set to a list of the most recent games. And then the view is updated to reflect that new state. This is what React does. Whenever state or props or both change, it will update the view for us, so that from our perspective, the view remains a pure function from state to DOM elements. This is all we need to care about. And so about that mysterious magical step 2, well, it isn't really that mysterious. What we need to do is fetch games from some sort of persistent storage, so that even if the app is closed by the user, no games are actually lost. Let's see how we can implement such a component. So the 7 wonders component isn't that difficult, really. Let's suppose you have a render game method that maps a single game defined as a domain data type to DOM elements. Then it's relatively easy to imagine how we can turn a list of game to a list of DOM elements. Just map on them. So assembling the UI for our page is, again, relatively easy. Our render function is simply a function that associates the state of our page, defined as a case class containing a list of games, to DOM elements, and these DOM elements are simply our page background component, and then our header component that we have discussed previously, and then a state.games.toVDOM array, which essentially takes an array of elements or a sequence of elements and turns it into a VDOM element by transforming each element to a VDOM element using a provided function. So it's essentially like map, except it is a bit more specific than map. But if you have a function to turn a single game into a DOM element, and then you have a list of games, then using toVDOM array, you have essentially a function to turn a list of games to a list of VDOM elements, or in that case, a single VDOM element. So it is actually, it is more like traverse than map. But anyway, pay no attention to the end backend bit that you see here. It's just a mistake, but we'll go over this on the next slide. To define our component, again, it's relatively easy. You just say that it is a Scala component whose props are the unit type, so this component actually accepts no prop, and whose render function is the render function defined on a backend class. Again, more on this on the next slide, and whose initial state is simply a state with no games in it. But then what we need to do in order to fetch our data from the external storage is to define the value for component did mount, which is the method that React will execute whenever this component is first rendered into the DOM. And the way you do this in Scala.js React, well, it's not the only way to do it, but the most maintainable way of doing it is by first defining a backend, which is just a class you provide in which you put all of your logic. So everything is in the same place. You have all the logic of your component in that backend class. And then you can tell Scala.js React to render whatever render method is defined on the backend, which is what we do when we say render backend and then pass it the backend class as a parameter. And also tell it that whenever this component is mounted, I want it to execute the component did mount callback that is defined on the backend itself. So the backend has a component did mount callback. And then we tell Scala.js React, well, this component, it has these props, this state, it has this render method defined on a backend, and when you render it into the DOM, I want you to call component did mount on that backend. Callbacks are essentially lazy futures or IO monads, whatever you are more familiar with. They're the data types that represent code that is to be executed by React when React chooses to. So these are pure descriptions of programs that can contain side effects. Speaking of side effects, now that we know what our component is going to look like, it's a good time to think about where is it going to fetch our actual data? Where is this data going? So the idea was to have a persistent storage for our Seven Wonders games that did not rely on a backend or an API. I didn't want to deploy a server to use that application, so it's still a pure client-side only application, but with some sort of persistence. This persistence layer is backed by IndexedDB. So IndexedDB is a transactional key value store for client-side data. It stores keys and values in object stores, and these object stores are persisted on the client side, which is how we can have games that remain even after the user has closed the application. It is organized into object stores that contains key value pairs, and these key value pairs are ordered by keys. So it supports simple operations like get a single key or get a range of keys, because keys are ordered, so you can tell it to retrieve keys within a certain range. And it also supports looking up values using their properties, using indices, which are essentially object stores whose keys are properties of objects in another object store, and whose values are keys that point to these objects. And it has an asynchronous and imperative API. So let's take a look at vanilla IndexedDB. IndexedDB is a transactional data store, so everything has to be done inside a transaction. The API is entirely callback based, so it is quite easy to end up with messy, nested levels of deeply nested code that is very hard to maintain. The idea is that every operation in IndexedDB return requests, which are objects that have callbacks that you need to reassign on every request, and this is how you get notified that your operation has succeeded. So if you want to put a value in an object store, you call the .put method. It will give you back an object, and then you override the onSuccess handler on that object. And when the callback that you provided is called, then it means that your operation has finished. The lifecycle of transactions in IndexedDB is entirely implicit, so you must use callbacks to extend a transaction after a successful operation. And there is no explicit way to commit a transaction. The idea is that if you don't extend the transaction immediately in the callback, and if you return to the event loop without extending the transaction, then the transaction is closed implicitly. And so this approach will expose you to a few pitfalls that can make it a bit tricky to develop IndexedDB applications. The first of these pitfalls is, how do you handle errors? So these messy nested callbacks right here are actually the best case scenario, because if you need to handle errors, because these assume that everything is going well, but if it doesn't and you need to handle errors properly, then not only you need to reassign the onSuccess callback for every operation, but you also need to override the onError callback for every operation. And then it gets really rapidly out of hand. The second pitfall, also related to error handling, is that not every error is conveyed by this this on-error callback. So if you try to insert a value and you use an unsupported value as a key, for example, you cannot use objects as keys. You can only use strings and numbers. And I think you can use the null also as a key, but I'm not exactly sure. Anyway, you can't put objects as keys. Well, if you try to do it, then one would expect that all errors are reported in the on-error callback, and that this console.error statement is going to be fired, but it never is. This is never triggered. Instead of having an error in the on-error callback like you would expect, you get an exception that is thrown synchronously from the place where you called tx.objectstore.put. So it is thrown immediately instead of being inside that asynchronous callback like you could expect. At least on Firefox, I'm not exactly sure whether it does this in all browsers, because I have to tell that IndexedDB is also an experimental API, so things are not quite settled yet. Another pitfall is the premature closing of transactions. So because the lifecycle of transaction is closely related to the event loop, if you try to mix asynchronous code like fetching data from another API with IndexedDB code, transaction may end up being closed implicitly, whereas you don't expect them to. So in that example, if you try to put something inside a store, or rather get something from a store, no, that's it. If you try to put something into a store and then in the onSuccess callback, wait for another promise to finish, like wait for an API call to finish or set timeout, then you essentially return to the event loop and your transaction is closed, which means that you can no longer do anything else with it, which means that your the next operation, the get operation, will never be executed, and neither the onSuccess callback or the on-error callback will be fired. As a consequence, it will be potentially unsafe to manipulate IndexedDB using a promise-based API. So this is an existing library that wraps all IndexedDB operations inside promises. It is possible to do it, and in most cases, it will look a lot nicer. But the thing is, if you mess it up and mix IndexedDB promises with other promises, such as a call to fetch or set timeout or whatever, then you get an error, and you cannot and your transaction is essentially closed implicitly. So these are all consequences of this implicit transaction lifecycle. Finally, the last pitfall is the way you create object stores in IndexedDB. So when you open a database, you need to provide a version, and then you get a single opportunity to create object store in indices by comparing the version you provided with the last seen version on the device. And you cannot manipulate stores or indices outside of this on-upgrade needed callback. And so what I've decided to do is try and write an interface for IndexedDB that minimizes the room for user error. I took inspiration from an existing Scala library called Doobie, which is a pure functional JDBC layer for Scala and Facades. And I took inspiration from it to create also a functional layer for IndexedDB that avoids most of these pitfalls. This API is structured with 3 main layers. The first one is really not that interesting. It's a straightforward facade to the JS API. So every trait is named exactly like the JavaScript class. Everything is still highly imperative. everything is still using callbacks, and everything is using nulls rather than Scala types. It's a facade that is very close to the JavaScript API. And then you have a second layer, which is a future-based API, which is essentially like the promise-based API we've seen earlier. It uses options instead of nulls. It uses futures instead of callbacks, but it still exposes you to a few pitfalls, and specifically to the premature closing of your transactions. If you mix IndexedDB futures with other futures, it's essentially the same issue with the promise-based API. You cannot mix IndexedDB code with other forms of asynchronous code, because if you do that, then the JavaScript runtime will close a transaction in the middle of it. And the way you create object stores and indices is still highly imperative. And finally, we have a third layer, which is a free monad-based API, in which object stores are parameterized by the type of data you store in them. And the mappings between your Scala types and your JS types that you store in IndexedDB are provided by type classes, very similar to what Doobie does using the read and write type classes, and also very similar to what Cersei does with the encoder and decoder type classes. So no more as instance of in your code. Notice that this layer also uses a new feature of Scala 3 called type class automatic derivation, which lets us derive automatically instances of object encoder and decoder Facades classes and subtypes, as long as their components themselves can be encoded or decoded. The idea of that free monad-based API, I'm sorry, I'm skipping this bit about the object stores management because it's not that important. The most important idea of that free monad-based API is that transactions are pure descriptions of IndexedDB programs. Transactions themselves have absolutely no effect until you interpret them into another monad, typically future or IO. And because they're monads, you can use map and flat map and traverse, and more useful combinators to build larger programs out of smaller ones. And because this is a dedicated transaction type, it is impossible to mix IndexedDB operation with other asynchronous operations. So you no longer have this issue with premature closing of transactions. Then this transaction, which is essentially a pure description of an IndexedDB program, can be interpreted into the effect monad of your choice using the appropriate backend, and the library currently provides backends for Future and Cats Effects IO. All right, let's wrap this up. So to implement the games page, what we need to do is define a few data types, our domain types. So in that case, what exactly is a game? Well, it's an ID, a date, a list of players, a game, which is, a state, which is a sum type. We derive object encoder and decoder for it, so we can automatically put it into object stores and retrieve them from object stores. Then we define a repository for our games using a trait. I'm using future in that case, but you can also define a more abstract repository using an abstract effect type. Then you open your database using db database.open and give it the name of your database and the object stores and indices that you want to create. Then you implement the games repository, your trait, which is, again, fairly straightforward. The only thing that the most interesting thing here is that the definition of a transaction and the moment you interpret it into futures are two separate steps. So again, it is transactions on their own have no effect, and this is the most important ID behind this IndexedDB layer. And then once we have an implemented repository, we can pass it to our component as a regular prop. And a trick that I like is to use a method defined on component, which is CMap constructor props, which is a way of modifying the props that a component accepts, which can be used to provide some sort of partial application to our component. So in that case, I'm fixing the repository so that the component itself can be called from the outside by providing no props, but from inside that component, it still has a single prop, which is our repository. And this repository can be used in our component did mount callback. That callback is executed whenever that component enters the DOM. And this is how essentially you end up with a page that loads data from IndexedDB and displays that data. Skipping over these parts, so this is roughly how to build a mobile-first web application using Scala.js React, which brings me to the conclusion, should you invest in this workflow, in this stack? Well, there is a lot to love about Scala.js React. Statically typed DOM, reusable components, algebraic data types, referentially transparent callbacks, all sorts of stuff. The massive ecosystem provided by both React, the ability to use existing React components, and the ability to use Scala libraries like Cats and Monocle. And there is a lot I haven't covered, like performance management, dependency injection, Cats integration. There is really a lot to love about this stack. And there is also more than one way to build type-safe web apps. So you might be interested into Slinky, another API for React and Scala.js, or into Laminar, or into ReasonML, and the list goes on. So I wasn't exactly sure how to conclude this, but there is one thing I know for certain. So let me tell it before I go. I think that whatever the solution you choose, be it Scala.js or PureScript or Elm or whatever, type-safe web applications are the future of web application development. And despite a few quirks like relatively large bundle size and well, that's all I can think of right now. So it's really not that a lot of quirks. I would choose this workflow any day over vanilla JavaScript for developing web applications. And that's it. Thank you for listening to me. And you can find all of this on GitHub. Also, please check out the, of course, Scala.js and Scala.js React repositories. And on my personal GitHub account, you will find on board games, well, the application itself and the slides for this talk. On Scala.js IDB, the IndexedDB layer that I was talking about, and on Scala 3 Next.js template, a template to get started building your own applications using React and Scala.js. That's it. Thanks a lot.
Hi, thank you so much for your presentation today. It looks like we don't, we might have a question coming in. Let me just double check for you. We do. So let's put that up on screen. Do you have any experience with Laminar, and can you compare it to Scala.js React?
I don't have any experience with Laminar. I've seen how this works, and I'm really interested in Laminar's approach to development. One thing that I would say is the nice thing about Scala.js React, or Slinky for that matter, is that there is a lot of value in being able to just use React components that already exist. The ecosystem that React has is absolutely huge, and it will make a difference if you're trying to build an application really quickly. But if you have the time and money to invest in building your own UI kit from scratch with your own design language, then it doesn't really matter if there isn't any readily available components for it yet. I don't know of I don't know if there are many ready-to-use components with Laminar, and so I would say this is a plus on the React side. But aside from that, I think Laminar looks great, and I will probably play around with it someday.
Fantastic. Thank you. We have one more question. How complex is it to set up Next.js with Scala.js?
It is relatively easy. The thing about Next.js is that it expects you to provide pages in a specific folder because it uses file system routing. But Scala.js can output JavaScript in any file you would like. So what I did with this Next.js template is to tell Scala.js to output a single JavaScript file per page, and then use a Webpack alias so that files from the target repository of Scala.js can easily be imported in the page folder, if that makes sense. The overall process is relatively easy. The thing is, you will need to develop bindings for any feature of Next.js that you want to use. So I have personally developed bindings for the router and the next link components because I needed them, and I think navigation is an essential part of many apps. But I haven't developed bindings for the image component of Next.js, for example. So if you need that, you will probably need to develop the binding yourself. Or maybe I will develop it and add it to the template. But yeah, it is easy, but as with any JavaScript library, you need to provide the bindings if you want to call these libraries from the Scala side.
Fantastic. Thank you. It looks like that's all the questions we have for real this time. So I hope you get to enjoy the remainder of the conference and have a lovely rest of the day.
Thank you. Thank you all.